So 612 is isentropic efficiencies of turbines, nozzles, compressors, and pumps. So you guys are probably wondering, you're like, that's a lot of things, right? And you are correct, that is a lot of things. But it is extremely important that we do this chapter because all of these are what you will see in basically every cycle in the next class. Chapter 8 through 10 is all things consisting of this: compressors, turbines, pumps, nozzles, right? And so you need to know how, whenever you see one, you need to know how, number one, you need to know the relationships between work, heat transfer. You need to know how the isentropic efficiencies work. So we're going to introduce that here, isentropic efficiency. So it says, engineers make frequent use of efficiencies and many different efficiency definitions are employed. In the present section, isentropic efficiencies for turbines, nozzles, compressors, pumps are introduced. Isentropic efficiencies involve a comparison between the actual performance of a device and the performance that would be achieved under idealized circumstances for the same inlet and same exit pressure. These efficiencies are frequently used in the subsequent sections, so that last part, 100% true. Frequently used, every single problem. You will very rarely find a question in chapter 8 through 10 where you will not have to do something like this. I will go as to say you will have to do it for every question. So, what does isentropic efficiency mean? Okay, so what it means is that we have some level of performance, right? And by the way, so isentropic, as we all know, it means that essentially delta S is equal to 0, right? There's no change in entropy. And how we got no change in entropy was because there was no heat transfer, right? Because remember, there was no change in entropy from heat transfer. And there was also no entropy change or entropy produced by the process. So both of these went away, and that's how we got isentropic, an isentropic process. So when we say isentropic efficiency, that's the implication, is that those things are gone, right? And so essentially what this is that an isentropic turbine, let's just talk with that first. An isentropic turbine would be the highest performance you could possibly get from a turbine, right? Because there was no entropy gained at all. It's just S1 is equal to S2, and it's the best you can possibly get. But obviously that's not how real world works. Real world, your turbines have, some heat loss. Your turbine blades have a little bit of friction as the air hits it, or a stream hits it. So there's a lot of things to take into account here. There's also frictional losses on the shaft that powers that goes to the generator. So there's a lot of things here. But when we say isentropic, that's what we mean, is that it's perfect. In the real one, it is not. So how you do isentropic efficiency is you would say eta. You could call it eta T or eta turbine, but I always do eta capital T or eta turbine, would be equal to. This would be the normal one. So this is the actual. I guess I should write actual then. We'll do that. So this will be actual. The actual work of the turbine. So work over perfect turbine work, right? So let me get rid of the T. So essentially it's the actual work we produce divided by the perfect work. And really fast, this number will always be less than 1 because obviously your actual work can never be greater than your perfect work, right? It is 1. This right here is 1. This right here is something else, right? It is the perfect. So you'll always get this number less than 1. It'll be between 0 and 1. So that is what we are dealing with when we talk about any of these, by the way. This is any of them. Any of them is just like this. Now, we have these right here, we'll get to in just a minute, but they are actually in a weird reverse. But you have to remember what compressors and pumps are doing in order to get this equation right. But we'll get that in just a second. Those aren't exactly the same. So it says, to introduce the isentropic turbine efficiency, refer to figure 611, which shows a turbine expansion on a Mollier diagram. I will not go to a Mollier diagram because it's it's something that's way too okay, it's not really complicated, but it's kind of hard to read, and you don't really get much out of it. So we're not worried about that. I'll show it at the end, maybe. And it says, the state of matter entering the turbine and the exit pressure are fixed. Heat transfer between the turbine and surroundings is ignored, and as are kinetic and potential energy effects. With these assumptions, the mass and energy rate balance reduces to this. So we've seen this before. Essentially, with everything else neglected, heat transfer, kinetic potential, and all that stuff gone, this is what you get when you look for the work of a turbine, right? It's very simply mass times H1 minus H2. Pretty straightforward. And then it says, since state 1 is fixed, the specific enthalpy H1 is known. Accordingly, the value of work depends on the specific enthalpy of H2 only, and increases as H2 is reduced. So essentially, think about it this way, is that the further apart these two values are off, right? The further apart these two are, the greater this number is, and therefore the greater the work is. And the reason why that works is because works, no pun intended. The reason why it works is that essentially if we have a turbine and heat transfer is neglected, right, and all other frictional losses and kinetic energy and all that stuff are neglected, that means that the only energy coming in and out of the system is work, the enthalpy coming in, and the enthalpy leaving, which means that if the enthalpy leaving is really low, it means that the energy difference between H1 and H2 had to go to work, right? All energy left as work instead of as heat transfer, right? Because sometimes a portion of it leaves as heat transfer. So work would be there. Essentially, some of this is left as this, and that's why this number is low. And so the further apart we can get H1 minus H2, the more work we can create, right? So it says, the maximum value for turbine work corresponds to the smallest allowed value for the specific enthalpy at the turbine exit. This can be determined using the second law as follows. Since there's no heat transfer, the allowed exit states are constrained by this. Right? So we've seen this before. Sigma has to be equal to delta S, which this has to be greater than 0. Okay? And it says, because the entropy production cannot be negative, states with S2 as less than S1 are not accessible in an adiabatic expansion. The only states that can actually be attained adiabatically are those S2 greater than S1. So that is simply what we're saying is here. If we're looking at this chart right here, that is simply saying the following. With adiabatic expansion, which is what I'm about to show you, this would be pressure 1, and this would be pressure 2 through a turbine. Adiabatic expansion through a turbine. Essentially what we're saying is that the only ones that can be accessible, I know it's kind of a weird sideways drawing, are the ones on this side. You cannot have it to where S2 is less than S1, right? It doesn't work. Because entropy production is positive, therefore we added entropy through the process, so it has to be greater. Basically what it's saying is you can't go this way on the chart from an entropy drop, like an expansion of this, right? So all the ones that are accessible are this way, or straight up and down, which is what we would call an isentropic process, right? So that's what they're saying here. And then it says the states labeled 2s on figure 611 would be obtained only in the limit of no internal irreversibility. So this is where the notation, you have to learn this. So I'm going to draw my chart again here, and I'm going to draw it a little bit better this time. So, how we do these states now, right? So how we do this now, and this is going to be a TS diagram for the people wondering. So, S and T. So how you show the perfect state is you mark it with S. So it's supposed to be like state 2 isentropic. So if we did state 1, and it looked like this. I know it's not a straight line, but you get the idea. State 1 is here. State 2 is here. This would be state 2s because it is the isentropic process. The actual state 2 would be somewhere this way. We don't know how far that way because I don't have any numbers, right? But it's over here somewhere. And so that's the actual one. So this is 1 to 2s. And what 1 to 2s represents is no change in entropy. It is state S1 is equal to S2. Right here. Right? So, does everybody understand that? Like I said, it's very important that we get this. Okay. So, and essentially what this represents, what this represents is more work actually produced, right? State 1 to 2s is going to produce more work than states 1 to 2. And so this is essentially where we're at. Is that this is essentially that is the perfect process. This is the one that we're actually doing, right? So hopefully you get that. So 2s means the isentropic. And by the way, anything with an S. So you could run into a compressor or a pump that states 3 to 4, and it's only after. There is no 1s, because 1 is a state going in always at these conditions. It's only after a turbine, compressor, pump, or a nozzle or a diffuser. Those are the only ones that have, and it's always after. So for example, if we did, I'm going to draw a Rankine cycle. So this is the very first cycle in Thermo 2. So state 3 would be here. And then this right here would be state 4s. And right in between this process is a pump. In a Rankine cycle, it's a pump. So essentially state 4s. And then, as we've done this example before, the actual one would be this way. Because remember, it can't go the other way. So 4 actual would be that way. So this right here is a basic Rankine cycle. And so it's only after a process like a pump or a turbine or something that you get an S. All right. So let's go ahead and move on. Only after. So then it says, this corresponds to an isentropic expansion through the turbine. For fixed exit pressure, the specific enthalpy H2 decreases as the specific entropy decreases. Therefore, the smallest allowed value for H2 corresponds to the smallest H2 or 2s, right, which corresponds to the smallest entropy change. And so the maximum turbine work is as follows. It is H1 minus H2s. So this is the most turbine work you can possibly get out of the cycle, or out of that process. This is the most you can get. So all of your energy, nothing left is heat transfer. There are no internal reversibilities. And the difference between your entry state and your exit state is simply the work leaving, right? There's no other things involved. It said in an actual expansion through the turbine, H2 will always be greater than H2s, and thus less work than the maximum would be developed. This difference can be gauged by the isentropic turbine efficiency shown here. So this right here, as I showed earlier, is the isentropic turbine efficiency. It is the work of the control volume of the actual over the work of the control volume of the isentropic. So therefore you get H1 minus H2 over H1 minus H2s. Okay? And then it says, both the numerator and the denominator of this expression are evaluated for the same inlet state and the same exit pressure. The value of eta t, so that's eta t, is typically between 0.7 and 0.9, so this is 70 to 90%. All right, so real fast, we're going to knock one of these out on Paint, because I want to show you, because once you figure out how to do one of them, they're all very similar in how you do them. So I'm going to knock one of these out. We might end up doing 2 of these today. But it's important that we understand it, because the whole next class, that's all you do, is you do this process constantly. It is very tedious. The Thermo 2 is very tedious. I will not lie about that. But I think you guys will come to appreciate Thermo 2 a lot. I think Thermo 1 is generally a drag. Thermo 2 is actually a lot of fun. So I think you might enjoy it. But what do I know? All right. So it says, a steam turbine operates at steady state with inlet conditions of pressure 1 is 5 bar and T1 is 320. So we were given some things already. So let's go. Givens. So first one, we were given a pressure P1 is equal to 5 bar. T1 is equal to 320C. And then it says steam leaves the turbine at a pressure of 1 bar. So we were given pressure 2 of 1 bar, right? And then it says there's no significant heat transfer between the turbine and its surroundings, which means we can say that Q is equal to 0. And kinetic and potential energy changes between the inlet and exit are negligible. So we have K is equal to 0. I'm just going to call it K, and P is equal to 0. So kinetic and potential energy effects are 0. I'm getting blown up on my phone, by the way. I have no idea what's going on. Sorry if you can hear that. It says if the isentropic turbine efficiency is 75%, determine the work developed per unit mass of steam flowing through the turbine. So what we are trying to find, the work of the turbine. That is our goal. So to do that, though, let's go ahead and write some equations out. So these would be the first things you do, equations. So one equation you should probably know is that work is equal to H1 minus H2, right? Or work S is equal to H1 minus H2S, right? So these are two things that we might need to know. And then there's one more thing that we need to know, which is A to T. So I'm just going to write it as NT is equal to H1 minus H2 divided by H1 minus H2S, okay? So these are the equations that you might need to know for a question like this, okay? Now let's start with getting some things that we need to know. So we're going to start here. State 1. So state 1. Tanner, if you're here, since you said you got it like 20 minutes ago, tell me what we're supposed to find here. What are we doing?
So we could start in the enthalpy, state and specific entropy.
I agree. So it means we need to go to the tables. And since we're in SI units and we were given steam, we go to the water tables. But first we need to find out where it is located. Now, as a rule of thumb, unless stated, going into a turbine is almost certainly superheated. It would be dumb to do it any other way. It has to be over the saturated mark or else it'll corrode the blades. You don't want a lot of water going through. So over superheated means you don't have any, right? Or in superheated, you mean you don't have any. So they said we're at 5 bar, I'm pretty sure, and 320. So we can check 5 bar. We are way higher than that, which is exactly how you would expect it to be. So 5 bar, 320. That means we go to the superheated tables as usual. And we go here, 5 bar. And then we go to 320. So our numbers, it looks like we want 3105. So I'm going to do that really fast on the screen. So we have H1 is equal to 3105.6. And then we also want specific entropy. So S1 is equal to 7.5308. And this would be in kilojoules per kilogram, and this one would be in kilojoules per kilogram Kelvin, right? So this is what we've got, and that is correct. That is what we wanted, right? So now, we have found state 1's things, and now you guys might be wondering, we don't need anything else. I can tell you that we don't need anything else because this isn't like a volume process. It's also a open system, which means we don't even need internal energy. In Thermo 2, you will use internal energy every now and again, but for the most part, it's open systems like this. So you'll have to just work with those when you get there. Now, next part, we have to do state 2. So what do we know about state 2? Well, we know the pressure, right? We know P2 is equal to 1 bar. That is all we know, right? Would you guys agree? That is the only thing we know. But to solve through the turbine, what assumption can we make?
is safe to assume because it mentions that steam exit that the quality state 2 is going to be 1 or greater, or in this repeated reading still.
We do not know that for a fact. We do not know. But there's something we can do, right? So what is the best case? So this is the pattern that we have to follow when we do these, and this is important why we do it now, is because when we go through a turbine, the first thing you should always do is assume isentropic, right? Assume isentropic immediately. So if I were to assume isentropic, Michael, what would I write here? It's an isentropic turbine.
S2 is equal to S1.
Correct. S2 is equal to S1. This is the very first thing you should always do when doing turbine, compressor, pump, all of that stuff. It's this, because I'm going to show you why you do this in just a second, but it'll make a lot more sense, I promise. So we assume it's perfect. Off the jump, we go, all right, it's a perfect turbine. Wonderful. So now that we know S1 is equal to S2, what we can do is we go to the tables, right? We know it exits at 1 bar, right? Exits at 1 bar. So we go back here and we look at 1 bar and we go check our entropy value. Does our entropy value fit there? 7.5308. Let me go back. You said we are higher than that, which means that we are where?
We're going to be in the superheated table.
Correct. And the reason, so real fast, you always have to, so for turbines especially, you always have to check because, okay, more often than not, you'll be in this region, but there are times where it does slip in and you're still superheated. So you do have to be very careful. Plenty of people make that mistake where they assume and it never works out. So then we have to go to 1 bar, right? And then we have to go and find an entropy value that is close here. So I'm going to pull out the calculator and get us a actual answer here. Maybe. We'll see if my interpolation still works. Although if it doesn't work in just a second, I'll do something else. I'll just look at the answer. So our number, I have to pull it open and move it over here so I can do it. So it says our entropy is 7.5308. So x1 we will call as 7.4. So what I'm doing is I'm doing the linear interpolation. So I'm interpolating between the lines here. So I'm going to do x1 7.4668. y1 will be trying to find an enthalpy, so 2796.2. And then we also have 7.83, so 7.8343. And then y2 is going to be 2875.3. And then x3 is our entropy, which is 7.5308. And you get a value of something about that doesn't seem right. Actually, no, it does. That's all right. Actually, no, it's not. I read up a line. Yep. It was taking too long. So essentially what you're supposed to do is you're just supposed to interpolate between here because our number is in between here. I accidentally read up one of these lines when I wasn't supposed to. Got to be careful. So I will try and do that again because I am bad. But this is why double checking it afterward is always a good idea, because if you just go by what's on your calculator, you will make an error like that. And it's hard as a grader to see that error in real time. Like when you're looking at it, it's really hard. Because, you might just say like, oh man, he must have just guessed it really bad. But it is not so. So it says that our enthalpy is 2743.01. So I'm going to go ahead and write that down. So I'm bringing it back here. Maybe. Okay. 27. So we did a check here, right? So what enthalpy did I just find?
H2S.
H2S. Very good. Usually that gets people. So this is H2S, and that is because we found it using the assumption that S1 was equal to S2. We found it using the isentropic assumption. So that is 2743.01 kilojoules per kilogram. So that right here is our H2S value. Now, knowing this, how can we possibly find our regular enthalpy value? Which, by the way, what we're about to do is how you find basically all of them. This process that we are going through right now is how you find basically every turbine. This is how you solve through all of them. If you remember these steps, you'll never be lost. So we can use this equation right here. Because if you look, we have H1, we have H2S, and we were also given a turbine efficiency of 75%, which means we have A to T. If you maneuver this and solve for it, what you will find is you will find H2, which is the actual. And so I've memorized how these transformations look. At least we'll see if I did or not. But it should be H2 is equal to H1 minus 0.75 times, although I'm going to put it in regular terms here. I'll put it in the normal terms. A to T times H1 minus H2S. So this right here is the transformation when you maneuver it around. And so when you do this, you will get H2 is equal to 3105.6 minus, I was doing the compressor one, 0.75 times 3105.6 minus our value, which is 2743.01. And once you do that, you get an answer. And your value for H2 should be, let's go ahead and do this really fast. So 0.75 times 3105.6 minus 2743.01. And then you do 3105.6 minus second answer. And you get 2833 as an answer. Now, really fast, does that number make sense? Does this number make sense?
Yes, it couldn't be lower than H2S.
Correct. This is the furthest apart from H1 that we can possibly get in terms of enthalpy difference. This number is closer to H1, which means that we lost some potential due to some irreversibilities, essentially. So there was some entropy gain. It was due to irreversibilities in the system, so we lost a little bit of potential of what we could have made, right? So this one makes perfect sense. It is closer together to H1 than this one is. So this is least amount of work. And so what the question is asking for, the question in this section, what it was asking for, so solution, it was asking for determine the work developed per unit mass of steam flowing through the turbine. So whenever they ask that, they are asking for the actual work. They're never really concerned with, I don't think there's ever a time where they ask you for the isentropic work, because isentropic work it's made up. It's not something you can actually achieve. So whenever they ask you for the work of the turbine, it's generally, unless they tell you the turbine is isentropic, and it doesn't give you an efficiency, it means the real work. So you would say work is then equal to what? You would say H1 minus H2. And by doing that, you would end up with 3105.6 minus 2833.66. And you would get 272, it looks like. It's about 272. And this would be kilojoules per kilogram. And if you subtracted and found this difference, it would be greater. And it would be greater by a factor of this, 75%, essentially. It would be greater by that, or 25%. So let's go check the answer. I'm assuming we did it right. Let's take a look. Yep, 271.95. I got 271.94. So this right here is the process for every turbine that you will ever face. I promise you. Now, there are times where you'll have kinetic and potential energy maybe in the turbine. Very rarely, though, is it ever taken into account. But if you do, obviously there's maybe like one more step that you have to do. But essentially, this is the process. This is what you do. You find the stuff at state 1, you do S1 equal to S2, you find H2S. Now, a lot of the times, this right here, H2S will not, so H2 will not lie in the superheated region. There will be times where you'll say, you'll be like, well, SF, S2, and then this is SG, right? You'll say, it has a quality. So then you'll use this, just like you did before, to find X2S. So quality of 2S. So this would be S2S minus SF over SG minus SF. So you would find it the exact same way you did before, like using volume and entropy, except that now it'd be X2S. And then you would from finding X2S, you would find H2S using the equation, right? And then once you have H2S, you just plug it into here. It's the exact same for every turbine. So as long as you have that process down, you should be in good shape. But we'll get much more practice with it, I am sure. So now we have done that. Oh my God, give me 1 second. I'm getting a phone call and I'm going to hang up. All right. I'm actually excited. I got a text that said my coffee cup has arrived. It's been like half a month that I ordered it. Like, Jesus, man. How long does it take? All right. So this is the same question. We're not going to do that one. We're going to move on to a nozzle. So nozzle efficiency. So it says this is a similar approach to that for turbines can be introduce the isentropic efficiency of nozzles operating at steady state. So the isentropic nozzle efficiency is defined as the ratio of the actual specific kinetic energy of the gas leaving the nozzle to the kinetic energy at the exit that would be achieved in an isentropic expansion. So essentially what this is saying, and I know like they just, went at it. Essentially what it is saying is the following, is that in this nozzle, which I'm going to draw right here, right? This is the nozzle. In this nozzle, when it comes out this side at V2, which is velocity 2, essentially what do we want out of this, right? Out of a nozzle, we want the velocity. That's the important thing, right? Just like a turbine, we want the work. We want velocity 2 because that is essentially what is giving us our thrust, right? For like planes, for like jet engine cycles, this is what's giving us the thrust. We want this. We want velocity 2 to be higher than velocity 1 by a high level, by a pretty good margin. And so essentially what this is saying is that the efficiency of a nozzle, I'm just going to call it NOS, efficiency of a nozzle is more or less the velocity 2 of the actual divided by the velocity 2 of the, although it's squared, right? But essentially it's the velocity squared of the actual divided by the velocity squared of the isentropic. And the isentropic here is going to be without friction. Essentially there's heat transfer in here, no heat transfer, no friction. It's going to be the same way as we did the other one. Although I can tell you I don't think I've ever actually had to use this, but maybe on your homework you will. I don't remember, but I've never had to use this for Thermo 2. We always assume the isentropic efficiency of a nozzle is 100%, and there's a reason why. Is because nozzles are generally 95% or more are common. So basically what it's saying is the following, is that nozzles, generally speaking, don't have a lot of heat transfer because think about it, like let's use your garden hose for an example, which has a nozzle on it. It's essentially, there's no heat transfer really, right? So you would say negative to that. The only thing in there that is causing it is friction. Friction between the sides of the, the interior. And if they're well designed and, very smooth, you can reduce the friction by quite a bit. And because nozzles aren't very big, there are some big nozzles out there. Don't get me wrong. There are ones that are pretty big. But generally speaking, they're not very big in like, commercial, not very big. Therefore, it doesn't have a long time for friction to build up and really start losing, losing velocity at the end. Because friction, or the outside of the nozzle is kind of a function of like how much friction had a chance to build up against it, right, over time. And so it didn't. It didn't have a lot of time, therefore it's pretty high. So nozzle efficiency is 95% or more. So generally in Thermo 2, we usually just say they're isentropic, because the difference between this velocity and, like, let's say a nozzle's 99% efficient is so small that it doesn't really even, it's not really interesting to us, right? All right. I mean, we could do this one, but I don't think we should, honestly. You probably have one on your homework. So if you do struggle, right here is the book. Come to this example. I want to move on to the compressor, but right here is the example 613, and you can see. I don't remember if it's on the homework or not, but essentially how you'll solve this one is like you did before. You would just say Q minus W, right? Go away. Plus, and then you'd write in your kinetic and potential energy and all that, and you would just solve around for things at the second state, more or less. It's the same as before. But now we're going to move on to pump and compressor. So this is the one I mentioned earlier that can get a bit confusing. And maybe not confusing is the right word, but tricky. So it says the form of the isentropic efficiency for compressors and pumps is taken up next. Refer to figure 612, which shows a compression process on a Mollier diagram. We will not do that. The state of the matter entering the compressor and the exit pressure are fixed. For negligible heat transfer and with the surroundings and no appreciable kinetic and potential energy effects, the work input per unit mass is the following. So it's the exact same as the one before, except it is flipped. So this is the reverse. And the reason why it's the reverse is because when you come out of a compressor, you are hotter, higher pressure, right? As you guys probably might know, like, if you come out, if something's getting compressed, you're going higher in pressure. It's always hotter at the exit, which means that what? Enthalpy, which is a function of temperature and pressure, goes higher, which means that if you want this quantity to be positive, you would have to put 2 first. And because it's a compressor, and we know that we're putting in work, compressors don't make work, they require it, which is why there's a negative in front of this work, because it's a negative work. It's going in to try and get it compressed up, right? So H2 minus H1 is equal to the work going in for a compressor, reversed. Then it says, since state 1 is fixed, the specific enthalpy H1 is known. Accordingly, the value of the work input depends on the specific enthalpy at the exit, H2. The above expression shows that the magnitude of the work input decreases as H2 decreases. The minimum work input corresponds to the smallest allowed value for the specific enthalpy at the compressor exit. With the similar reasoning for the turbine, the smallest allowed enthalpy at the exit state would be achieved in an isentropic compression from the specified inlet state to the specified exit pressure. The minimum work is therefore given as this. So, really fast, we have flipped now. And I will talk about why we flipped in just a second, but I'm going to draw a little quick diagram. So, over here, how a compressor generally looks in Chapter 10, which is refrigeration, it generally looks like this on a TS diagram. So it draws the same way as a Rankine, but essentially it kind of looks like the opposite. So, the compressor, once again, very similar to a turbine that has blades in there, right? And it's like spinning it up. Or it depends on what type of compressor, I guess. But we're talking about this. This would be state 1. And then state 2 is a straight line up. So this is the inverse. And this would be 2S. And then 2 would be over here somewhere, right? So this right here is how a compressor would look in in this class on a TS diagram. P2 is up here, so the high pressure is there now, and P1 is the low pressure. So essentially it's like an inverse turbine, which that's how I like to talk about it. I like to call it that, but it's a simplification. Essentially it's an inverse turbine in a process-wise. The high pressure is now at the top of the diagram. The low pressure, or the second state after, is now going higher in pressure. The state entering was lower. So this is what it looks like. Now, really fast, this is why I wanted to show this one, because this is where people often get confused. So when we look at the efficiency of a compressor, right here, what you will notice is what? What has flipped on this one? Can anybody see on this equation? What has flipped? Yes, so the numerator and denominator have flipped. Essentially, the bottom now is the maximum work required. The top is the minimum work required, and this was specifically done to keep the value under 1. So this is still an efficiency, which efficiencies are under 1. So essentially, at the top, this is the perfect. So for compressors and pumps, the top is the perfect state, and the bottom is the lowest one. And the reason is because the top, the perfect compressor, has the lowest amount of work input. You have to think of it, you have to remember what you're dealing with when you look at this. Like, you can't think of it as a turbine or else you will flip it. And a lot of people do this. They'll get an efficiency that's like 1.5 or something, and they don't understand why. It's because of this. You have to make sure you flip it. So the minimum work at the top, maximum work at the bottom. But in this case, obviously, you don't want the maximum work, right? It's a compressor. You don't want your power requirements for the compressor to be high, right? Because then you're wasting power in a compressor. You want them to be low, which is why H2S is the minimum required. So, all right. But what's funny is that they kind of solve the same way, which is pretty funny, is that they solve very similar to this one, and I'm not going to actually I might not solve states really fast, but I am going to do like a little bit of this, so we have a few minutes. Let me get rid of this. But they solve very similar to a turbine in a lot of ways. So I'm going to go ahead and remove. Oh, that's the other one. Funny. Oop. All right. Oh, come on. Yep. Oh, wait, it says example 6.8, really? Oh, I have to actually know what those are. Oh, I guess it's right here. Never mind. So I can still do it. Here, I'll bring this over to the other screen and I'll just talk through it. I was gonna say, like, I didn't know it doesn't tell us what the input conditions are, but I guess it doesn't really matter. I can look at it. So right here, I'm going to just tell you what it says. It says refrigerant 22, so it's compressed adiabatically at steady state from a specified inlet state to a specified exit state. So what they are telling you is this. If you read the question, which we'd have to go back to, I don't really want to go back too much, but these are the givens. And you would just read the question normally, just like before. If you look at the TS diagram here, we are at a pressure of 3.5 bar and a temperature of -5 degrees C. So P1 is 3.5 bar. T1 is equal to -5. And then it says that state 2, right? So P2 is equal to 14 bar. And that's pretty much all we're going to know from the start. So I'm going to go ahead and write out the steps since we don't have time to get the actual question. But the steps to complete, right? So your first step would be as follows. It would be find H1 and S1. Similar as before, right? H1 and S1. Step 2, assume isentropic. So this is S1 equals to S2S, right? And then you do the same thing as before. Check what state you were in, or what phase. Is it saturated? But I will tell you, for a compressor, it will always be superheated. There's no other way. It can't be anything else, because you cannot put liquid into a compressor. So that means at minimum, state 1 will be right on the saturated vapor line. Or you can't put a lot in there, at least. And then if you go straight up from here, or on an actual, you'll go up to the right. There's no way. It can never go back to saturated. So it's always going to be superheated at the check. So, but I'm just going to say this is a good habit. Check the state. So this will be superheated, etc. Then find H2S using whatever you have to do, which would be, for this one, you would look in the superheated tables and you would find S2S. You would find S2S in the superheated tables at 14 bar. At P2. Then 5, using the compressor efficiency, find H2, the actual value of H2. Instead of, H2S. This would be the actual value. Now, the equation, so it would be use this. So if you want to remember the flip, like how it maneuvers around after you do it, what it is the following. It's H2 is equal to H1 plus, and then you do H2S minus H1 and divided by eta C. So this would be your equation. So just like the turbine one, the reason how I remember it is that they change signs. The turbine one subtracts, the compressor one adds, and you move the efficiency under the quantity. That's the difference between them, and this is how it maneuvers around. And if you did this, you would find the actual enthalpy of state 2. And from there, you could just find the work, right? The work of the compressor is equal to H2 minus H1. Pretty simple, right? So this is the exact same steps that you do for the turbine and the compressor. They are basically the same. Now, before we mosey on out of here, I think they're going to talk about a pump really fast. Oh, no. Okay, I guess they don't. So pumps and compressors are the exact... They're not quite the exact same in practice. And so this stuff is right? This stuff is correct. But there's a trick that we'll get to. But essentially, there's a trick for pumps where you can represent pumps as the following. You can essentially say the work of a pump is equal to... I think it's, it's this. So let's say the pump is between states 1 and 2. So you would do H2 minus H1, which is the work of the pump, but it's also equal to V, so it would be V2, V1, times the change in pressure. Because remember, this is essentially the work of a pump, right? It is the change in pressure times the volume, right? And then you would say P2 minus P1. And so what this is called is the perfect pump equation. So this is for an isentropic pump right here. And so then you would say H2 is, or this would be H2S, sorry. And H2 is then equal to H1 plus V1, P2 minus P1. So this is how a pump works. And this is how this is how most people, I think everybody solves pumps, is that they do this equation right here, which is the perfect pump equation. And then you would find H2S, and then you would do the same thing you do before, is using H2S inside of the pump efficiency, and you'd get your answer. So that is the trick, I guess. But we are out of time, unfortunately, or fortunately, depending on your perspective. I'm going to go ahead and end this, and then you guys, we'll take attendance, and you guys can go.